correlators. And some of you might say, oh, isn't that old stuff I've worked on 25 years ago? And of course you are correct. But let me explain why we are coming back to the topic. In what we did 25 years ago, we were heavily using reciprocating-derived TFT, which is a three-dimensional TFT, and we were heavily using three-dimensional manifolds. By now, it's clear that the structure of coordinates, the mathematical structure, implies that these methods can only work for finitely semi-simple CFTs. But you're not the audience to be explained that there's a richer world of TFTs. So it is clear that these methods literally cannot work if we want to go beyond finitely semi-simple TFTs. These are logarithmic CFTs, and obviously there are more and very interesting TFTs around. There are TFTs with continuous spectrum around, and there are also homotopical TFTs around, which arise, for example, in the correspondence between TFTs and supersymmetric gauge theories. So it's time to enlarge the toolbox, and enlarging the toolbox means working in a more two-dimensional setting. And that's what I want to do. And in order to do this, I want to first put the problem into context and say what kind of problem I want to solve. Then we have to work a bit. So we've seen graphical calculus earlier in this conference. For example, we have seen it in Katrin Moisburger's talk. We need a variant of this graphical calculus. And the important point here is, and this is already a take-home message, if you have graphical calculi between different input data, they should be related if you have a relation between different input data. This could be, for example, tensor functors, but this could be something more general. And what I want to argue is that this relation between different graphical calculi captures the essence of CFT correlators in this sense. So let me start with the work. Good. So if you think about CFT, then definitely many of you think about an infinite dimensional algebra of local symmetries, a vertex algebra, but say you think about the Virasoro algebra, the corresponding vertex algebras, and then you're considering representations because the symmetry acts on states. Whatever this representation category should have as a mathematical structure, it should come with a grading. And whatever you want to do in CFT, the notion of a conformal block is an important notion. See, the Virasoro algebra, or more generally a vertex algebras, have always been essentially tools to encode differential equations. Differential equations on all surfaces. You consider the solutions of them. They are typically multi-valued solutions, and these solutions are, very roughly speaking, the conformal blocks. So they are multi-valued functions as the positions of the field insertions and of complex structures. And if you have a multi-valued function and you go around a non-trivial circle, you have monotomies. And these monotomies capture essential information on the functions. So what I want to argue is to establish the existence of correlation functions, it's enough to know these monotomies and to keep them under control. I'm not going to say I can compute these as functions of the moduli and of the insertion points. But I'm paid as a mathematician, so I think they can pay me if I'm establishing the existence of a consistent set of correlation functions. Yeah? And we cannot even parameterize the moduli space of complex structures for a curve of genus 274. So computing functions is not feasible anyhow in general. So we have to keep these monotomies, and conformal blocks obey factorization. And there is a mathematical tool which captures these monotomies, and that will be modular functors. But a local CFT, as we have seen it in several talks in this conference, is not just a system of conformal blocks. It means you want to determine correlators, correlation functions, but you want to do a bit more. I think in modern times, You want to consider it on surfaces with boundaries. You want to consider line defects. You want to do this not just because this is the title of the conference, because it gives insight. And you want to do two things, and let me emphasize on two things. You want to be able to say what are the bulk fields, what are the defect fields, how do boundary fields look like, what are boundary conditions. So we want to specify the field content, and then we want to find the correlators for this given field content as specific conformal blocks. They should be correlators, they should be functions, they should be single valued, and they should obey Sewing constraints. And this clearly needs more input than just conformal blocks, than just solving chi-reward identities. So how do I control these properties of the conformal blocks? I've explained to you that we have a vertex algebra encoding this, and in the simplest case this was a modular fusion categories. So we have seen fusion categories earlier today. Modular means non-degenerate braiding. And important is we can fuse representations. There is a braiding which is non-degenerate in a certain sense, and there is more structure, but let me emphasize non-degenerate means that if you combine left movers and right movers, then you get a category that is the Trinfeld center. So the Trinfeld center will appear. It has already appeared in several talks here, and it will appear when we combine left movers and right movers. And you will say now, how can he possibly talk later about boundary fields? Well, wait and see. Okay, so now these monotomies of these solutions of differential equations, they can be encoded in a gadget called modular functor. Now, actually, I want to work here with something which is a bit more enlarged. I want to work with an open-closed modular functor. And so how does it look like? I'm starting here from a category of cobordisms. And what does it mean? We have objects which are one manifolds, but these are not just disjoint unions of circles, and these are not just intervals, because we have open-closed, it means we have intervals. We also have the empty one manifolds. Then, between two monomorphisms, we have surfaces. And maybe you will say, wait, does he talk about two-dimensional TFT? No, I'm not doing it because I take really surfaces, not surfaces up to diffeomorphism, and I take diffeomorphisms, so homeomorphisms up to homotopy, as another layer of structure. And this is how I will keep track of the mapping class group, in the end, the modular group. So now I have to map this to certain things. Well, I have to map this to categories. And here's a work just for the experts in the audience. You might have expected functors, but it's much better to work with profunctors. And if you have questions, I will explain why I'm working with profunctors, but this is to be kept a bit apart in this talk. So we want to construct such a gadget, and I don't want to go into the formalisms, but I will construct concrete examples in this talk, and you're going to see how they work. So what I want to do concretely is the following thing. Suppose I have here this surface. This is a surface which has here a genus 1 component, it has a boundary of circle form, and it has two boundaries, ingoing boundaries, which are intervals. So really between these intervals there is a boundary condition to be discussed later. And to this our modular functor should assign categories, and well, in the case of an interval, it is known what we should assign. Suppose we start from some, and I'm saying here modular fusion category, it could be quite a bit more general. You should assign here the category C itself, and to S1 you should assign a category to Trinfeld center, which is also the natural cylinder category. Okay, so now what should we do with the worksheet? So what should be the data we need to specify to talk about a CFT correlator? So I take the same surface, and you see I have here two bulk insertions. These are not ordinary bulk fields, but these are bulk fields where defects can start and end. So they are more general even than ordinary order disorder field. They are multi-branched defects. And the picture you should keep in mind about what kind of fields we consider in the bulk is we don't have just a bulk field, we don't have just a disorder field, but we have here quite a couple of defects, defect lines which go in or out, and here can be different CFTs. So imagine, for example, based on the same chiral symmetry, this could be, for example, an A-type modular invariant or a D-type modular invariant, or even an exceptional one, to say it in old language. So what you see is that we are decorating here the two patches with the type of CFT we consider, and it's established for a quarter of a century that the right way to specify this is a special symmetric Frobenius algebra. Of course, I'm cheating. If I want to do non-semi-simple categories, I should say a bit different words, but I'm cheating here to give you some overview. And then between such different phases of CFTs, you can have defect lines. They will be labeled by bimodules over this Frobenius algebra, and point defects will be bimodule morphisms. So you see, I'm insisting we have a three-layered structure on the CFT side. And a three-layered structure needs its appropriate mathematical language. And I should say, before going to this, here you see I have also generalized boundary fields. So this is not a field that doesn't only change the boundary condition m into n, but it eats at the same time a defect line that separates the green phase from the blue phase, and we should find field objects for this as well. These are quite natural things you should consider. So you see our field content has to be quite general, and there has been enough progress to describe these boundary field objects and the bulk field objects explicitly. This is a comment for the more mathematically minded part of the audience. So the boundary fields will be described in terms of inner Homs, and the bulk fields are actually also inner Homs, but they are in functor categories. That's very well under control. This is nothing I will feed in, but this is something I will have to get out from our approach. So, okay. So, what do I want to do? You give me a worksheet of your choice. You choose the topology, you choose the decoration, so you choose the defect lines, you choose the decorations of this, so the phases here, what kind of defects between them, you choose these point-like couplings, and I have to give you a correlator. Yeah, that's the rule of the game. And in order to do this, I have to give a correlator which will be what? It will be a conformal block, which I'm describing in terms of this modular functor, and it will be a conformal block for the given insertions of these field objects at the boundaries. And these conformal blocks have to obey consistency constraints. I'm not just allowed to give you any element. They have to be compatible with suing, and suing is something this gadget BL knows, and knows in a mathematically well-defined way. And it has to be invariant under the mapping class group. If I just take a torus, you know, the partition function has to be modular invariant. Modular invariance is the modular group is the mapping class group of the torus. But here we have a problem. What if you have a topological defect? What is the relevant mapping class group? Do you require it to keep the defect point-wise fixed? Looks a bit too strong, right? If you Do you require it that it keeps the defect fixed, but it can move points on the defects? It's also too strong. Do you require it that it can be compensated by a homotopy of the defects? Looks like a very complicated definition. So what I have to explain to you, and this will take me quite some work to prepare it, is what is really the appropriate subgroup of the mapping class group in the presence of a defect configuration. And the situation is really much worse than I sketched, because suppose I have this situation. I'm considering a CFT on an annulus. And I'm considering a CFT on an annulus, and I have the same type of defects, and this defect here is a defect and its inverse, and the defect is invertible. Invertible means that if you fuse the defect with its dual, it's the invisible defect. So these two things should be the same. But if you look at this, here you think naively there's a Dehn twist, because you can turn the inner circle by 360 degrees. But you wouldn't expect a Dehn twist here. So is the Dehn twist in the mapping class group or not? So what is the mapping class group of a worldsheet with defects? This is one of the questions I want to answer. Okay. And now, in order to do this, I have to work. And I'm working with graphical calculus, and I'm doing this first at a level where you think, oh, where is the worldsheet? But actually, I'm doing this from local to global. I'm first doing a local calculus on disks, and then I will glue this together in the second step. So now there are two chapters where you have to see how the machinery is developed. Okay, so the stringnet modular functor, and stringnet is a way to avoid saying the word skein, Gerard. Okay, and is then a globalized version of this graphical calculus. Okay, so I want to do this in the following setting. I hear the word bicategory, and when I prepared the talk, I've been told saying the word bicategory will make me lose half of the audience, but I'm pretty sure this will not be true. What is a bicategory? Think about a category as a two-layered structure. So you have objects and morphisms. A bicategory is a three-layered structure. What do we have on a worldsheet? Well, we have faces of CFTs, defect lines, and point-like insertions on them. So naturally, it is a three-layered structure. And just think about this three-layered structure in a way that you would do it without thinking about complicated math terms. What you would agree is that if you're sitting here, if you're looking at defects between two different phases, then you have a two-layered structures. You have the possible defects and the point-like insertions on them. So you have here really for the homes, not vector spaces or sets, but you have rather categories themselves. And instead of giving you the definition of a category, let me give you an example, or two examples, and both will be relevant. One is the thing I use to decorate the worldsheet. So objects are simple special symmetric Frobenius algebras, and then I need a category between them, but you know what this category is. These are bimodules. So bimodules come with bimodule morphisms. So this is layer number 0. This is layer number 1 are bimodules. Layer number 2 are bimodule morphisms, 3 layers. Okay, then we have also our modular tensor category, and we don't need the full power of pivotal, and that will have advantages here. If you're given a tensor category, you can set up a bicategory in a very simple way. You simply say layer number 0 is just a single object. Then layer number 1 are the objects in C, and layer number 2 are morphisms in C. So I'm just shifting this and I'm adding nothing to 0. And this looks like an empty game of mathematicians, but it is actually useful. So what you see is we have two bicategories. One is the decorations of the worksheet, one are the chiral data. And to keep both in discussing CFT correlators is kind of reasonable.
Sorry.
Yeah.
What is the difference between a bi-category and a two-category?
Some people make a difference, and it's a question whether the composition needs associators or the composition is strict. Actually, this is a subtlety I will not comment on. We don't need strictness. So if you replace it in your mind by two category, you're absolutely in the game.
Okay.
Yeah. In general, very few categories in real life, very few bi-categories in real life are two categories. Yeah, so even two vector spaces are not two categories if you look carefully. But that's a different topic. And so let's visualize them. And there are two ways to visualize. And maybe since some of you have come across one way or the other, let me go through two of them. So one is called pasting diagrams. If you have a category, a morphism is presented by an arrow. A morphism from A to B is presented by an arrow from A to B. You can compose arrows. So you could compose this arrow and this arrow. Now, in a bi-category, you have morphisms between morphisms. And you can again compose them. And composing means you're pasting them. That's the name pasting diagram. Now, in this game, Poincaré duality is obviously always an option. So I can replace the two cells, which are labeled by here, the two morphisms, by vertices. I can replace the vertices here by two cells. So this green thing is labeled by A. And you can replace the one morphism by a line which is perpendicular to it. And we will work with the pasting diagrams. And if you think about this as a local piece of a worksheet where you have a CFT in a green phase, in a blue phase, and in a purple phase, and you have defect lines running between them, and you have here point-like insertions on the defects, you are in the game. And if you have such a bi-category, we need to add a bit more structure. First of all, in a bi-category, you have also duals. So we have here diagrams which look very much like the evaluation and co-evaluation diagrams. And they obey also the usual zigzag relations. We have also seen them earlier. And actually, sometimes they are called also here adjoints. And what we will require is that there is a pivotal structure in the sense that the left adjoint equals the right adjoint. So this way of changing a morphism is equal to this way of changing a morphism. Please think about this as something which implicitly imposes certain finiteness conditions. You know, an finite dimensional vector space is isomorphic to its bidual, an infinite dimensional one isn't. So we teach this even in our class Mathematics for Physicists. But maybe think about this as finiteness. So now the important thing about this pivotal structure is previously I was writing diagrams in this way, and I was saying I can compose here in one way, I can compose here in another way. This was in our previous diagrams here. Let me go back. Here I can compose in a horizontal way and I can compose in a vertical way. The important thing in our setting is that the diagrams can be changed. So really, we are working here not with morphisms which are presented by boxes, but by disks. And why by disks? Because the disks stand for invariant tensors. We've seen this in earlier talks. And in this setting, invariant tensors are cyclically invariant. So what we do here is a calculus for invariant tensors. So actually something which predates category theory by a century. So, and then we want to evaluate, to work with diagrams which are of this form, so we don't distinguish between in and out, but in a sense there's only a circle, and we want to set up a graphical calculus for this. This is helpful because we are doing CFT on oriented surfaces. So on an oriented surface, I know whether these things go counterclockwise or clockwise, but I don't know on an oriented surface what is locally right and what is locally up. Of course, you can ask, is there also CFT on unoriented surfaces? Yes, there is, and I'm not going to talk about it. For type 1 strings, this is something you need to understand. Okay, so how do you work with this type of thing? So, the basic gadget in the games are corollas. This is a corolla. So I'm not advertising here, doing advertisements in favor of the suffering German car industry. So, but you should notice that the corollas are labeled. And we label the two patches by what we use for the two patches. And we are so this would be phases of CFTs. The one-dimensional things are labeled by defects. Yeah, so we use the same labeling. But we do not label for the moment the center. You might be tempted to put a vector space of couplings to it. It's better to organize things differently. And now we want to evaluate such a diagram. So what is such a diagram? Consider these shaded disks as ingoing. And then this is here a disk. If you look at this disk locally, that's this configuration. If you look at this disk, this is this configuration, and the outside circle has exactly what you have here: blue, green, pink, and then you're back to blue. And this is a morphism, and you can compose morphisms. You can compose morphisms by inserting, for example, if you insert this disk into the shaded disk, you will get this one. And for those of you who have heard about operettas, this is not a coincidence. It's a variant of an E2 operetta that we study here. So that's to be kept also secret at this conference.
Sorry, Christoph.
Yeah?
So you are freely deforming now the defect lines.
Yes.
I thought you said at some point earlier that we have to define what kind of deformations are allowed to define the modular group.
Well, this is about what we call the mapping class group.
Right.
So, but your comment is extremely helpful. So let me use it to explain things in a bit more detail. So what this graphical calculus has is, if you change a bit the defect line, if you apply local homotopies to the disk, the value of this graphical calculus doesn't change. So you're building in a certain invariance, and if you take on top of this a proposition from topology that any global homotopy can be described by composing homotopies that are located on disks, we really have these homotopies in the game. But what I have to explain to you is which of these homotopies will preserve the correlators. And that will come later. Yeah. So and if you look at this, then you already guess that here to this corolla you should assign the vector space of cyclically invariant couplings. And what I'm not going to explain to you is how you're defining such cyclically invariant couplings in the context of a pivotal bicategory. It's not terribly complicated, and the experts in the audience have already understood how this goes. Yeah, it works, and then it's a good idea, if you have such a gadget, to see if you're given such a morphism like here, can you build up this morphism from more elementary morphisms? And this is a bit of a combinatorial problem. So, for example, you have this morphism here, you have a morphism here where you contract such a loop, so which amounts to a partial trace, and you have morphisms where the graphs inside the disk are not connected. And a non-connected one will give us a certain trouble, but it's necessary trouble. So any morphism can be composed by taking a composition of morphisms of these four types. This is a theorem I'm asking you to believe. Now, this is the theorem, and now I can simply decide to throw away the non-connected ones. This is something that happens in many instances. So I have a certain subcategory which will show up in a moment. And then I start to set up my graphical calculus, which takes a corolla and assigns to an object, to a corolla, the vector space of couplings, so the cyclically invariant tensors. And on morphisms, like for example this morphism, what do we do? Well, what we do is we cut this disk open. So you see, I cut it open here and here. Then this green line becomes this appears. This green line appears. We get an ordinary diagram in the ordinary calculus, and we can evaluate it, and it gives us a single morphism. And you have to sit down and do a bit of work and show that this doesn't depend on how you are cutting open these diagrams, but that needs a clear definition of what pivotal bicategory is, and I haven't explained this. But this is a mathematically clear object, and it allows you to work in a graphical way with cyclically invariant tensors, and if you have several of them in a disk, of contracting them. That's the idea. Good. So now comes the point. We are not working with a single input datum, but we want to change the input datum, because if we discuss CFTs, we have two things in the game. We have the decoration of phases of CFTs. What are the defects? What are the bimodules? And if I'm saying defects, I also mean boundaries. They are included. Yeah. So and we have the chiral data which come from the representation theory of the vertex algebra. So we have to see what happens if we have two such bicategory and we relate them. And well, how do we do this? Well, maybe first a comment here. Look, here I have produced from a monoidal category a bicategory. We've seen this morning how you relate two monoidal categories. These were monoidal functors. So we should have something which generalizes monoidal functors. So we have to do now something on the objects, but we have to map also here. And then we have here that if we take the composition, but this is the old tensor product. So if we take the composition and then map, it should be the same as first mapping and tensoring. And of course it is not the same. You need to choose some data which have been in Sakura's talk. And these data are here. This is an arrow as anything in category theory, and it has a direction. And I'm not taking necessarily an ISO. Okay, now you have to do the same game for the units, but maybe we don't talk about the units here. So there's a way to graphically represent this. So I'm here first mapping little f with my functor f, little g with my functor g, and then I have to compare it with the other direction where I first multiplied little f and little g, and then I mapped it. And you see this looks like a multiplication. And I'm not talking about a unit. Now, this graphical calculus is a bit fishy. It can be turned into a decent graphical calculus, and more or less you have seen a variant of this graphical calculus earlier in this conference in Katrin Meusburger's talk. Because really, if you want to do it decently, you work in a three-dimensional graphical calculus where you have a category, a functor which maps this. So here is mapping C to D, and then tensoring, and here is taking C and D, and then tensoring and then mapping it. And there is a natural transformation here, which is a singular point on this sheet. And this is a powerful calculus which makes all this graphical calculus rigorously and usable. I'm not going to use it here. I just want to give you a feeling that all this has very solid mathematical foundations. And if you look at this from this side here, you see that this is the multiplication. So really, the multiplication is appropriate, but I'm just drawing it on a complicated sheet. Good. Now, you can write down the axioms. And one of the axioms for a monoidal functor is an associativity axiom. And there's, of course, also naturality and something for units. And if you look at these diagrams, there is a kind of a very silly game in category theory. You take the diagrams, you reflect them, and you read them instead of from bottom to top, from top to bottom. If you do this, then you're getting not just a multiplication, but a co-multiplication. And that gives us, and I'm not claiming here that such an oblax structure or such a lax structure are invertible. And even if they are invertible, I don't want necessarily they to be inverses of each other. Now suppose we are given a natural transformation here. So we are given something which takes, in our application to CFT, a defect line F1, a defect line F2 up to Fn and Fm, and it fuses this, and fusion is associative, hence I'm writing this in this sloppy way. It fuses it and it spits out G1 up to Gn. Okay, now I'm applying the functor to it, which gives me a morphism from here to G of these things, but then I'm using my multiplication and my co-multiplication to get really a coupling from here to here. And this is an operation we call F conjugate. And these are structures you can consider on a functor, which are weaker than monoidal, a monoidal functor, as we have seen it in Sakura's talk earlier. Now, these things are nice because they allow to relate two different graphical calculi. So I take my corolla, I change the labels by changing A to F of A, the one morphism, so the defect according to how F acts, and then I have to assign for a natural transformation everything to a corolla, which is a morphism of vector spaces, and that's exactly this F conjugation. And now we know what it means that a graphical that a functor which has this lax and oblax structure preserves a graphical calculus. This is defined. So we know what it means to go from a bicategory, which are defect data, to a bicategory, which are chiral data. Okay. And now, when is it preserved? If you sit down, the first thing you do is, oh, it has to be nice to adjoints, or it has to be nice to duals, and it should be a pseudo-functor. So here, these two structures, I have the lax and the oblax structures are each other's inverses. So that's a strong requirement. And if you do this, then you find out that a rigid pseudo-functor preserves the graphical calculus. And I'm asking you to believe this. I'm not going through the proof. Not because the proof is terribly difficult, but it's simply too much work for now. And the situation that's actually relevant for CFT is a different one. What we require is that the lax monoidal structure and the oblax monoidal structure are really compatible. In a way, they are compatible for Frobenius algebras. So it's a generalization of Frobenius algebras. And if you distrust this two-dimensional graphical calculus, there are very beautiful pictures in three-dimensional graphical calculus. Actually, I'm very poor in imagining three-dimensional objects, so we were printing some of these things on a 3D printer just to be able to take them in our hands. And by the way, this 3D graphical calculus is borrowed from logic. It's has been first introduced in linear logic. So, okay. So, it is Frobenius. It is also separable. And if you know what a separable Frobenius algebra is, you will try, agree with the use of the word separable. Now, a rigid Frobenius functor does not preserve the complete graphical calculus, but it preserves the connected part. It preserves only those morphisms which are connected. We had several which weren't connected. So it preserves the connected graphical calculus. That needs, again, some work. And you might say, okay, that's not enough. It should preserve the graphical calculus. But we will see that actually this lack of respecting the complete graphical calculus is something we need for CFT. So now you see that what happens is, if I take two of these morphisms, and obviously this diagram is not connected. If we apply F conjugation, we map the morphism, but if we first apply the horizontal product and then we map it, then we have this morphism, and then we apply this F conjugation, which means we are concatenating with this product and this co-product, and then by naturality you can write it in this way, and you are getting this gadget here. If you've ever worked with Frobenius algebras, you know that this is something special. This will be, in the appropriate sense, an idempotent, and it will be an idempotent that we will compensate by this idempotence. Okay, so now what is this Frobenius functor that's relevant? I've hinted to it. It maps the bi-category of defect data to the bi-category of chiral data. It cannot do much on an object because there's a single object here, so to what else should it map a Frobenius algebra? It maps a bi-module to the underlying object, and it maps a morphism to the underlying morphism of bi-modules to the underlying morphism of objects. It's a forgetful functor. And it turns out that this forgetful functor for these separable Frobenius algebras is actually a Frobenius monoidal functor, and you can check that if you compose here the lax and the oblex constraint, you don't get the identity, but you get projectors. Okay, good. Now, let's quickly globalize this. So we have this for these two categories, both relevant for CFTs, and we construct separately a modular functor. We do this as usual. We take an oriented surface, we fix some boundary values, which are not just objects, but these are one morphisms, and between the objects there are objects of the bi-category. And then we take the vector space, which is freely generated, well, not by graphs, but by graphs which are colored, where the faces are colored, and then we mod out by local relations. This is, if you've seen the Levin-Venn stringnet models, this is the Levin-Venn stringnet model, but just done for a bi-category. So we allow colors to the surfaces. Okay. So you can do this a bit more formally, and I want to make one. So you set up an evaluation functor, and then the stringnet is actually a co-limit. So if you want to do this with some complex valued CFTs, which is something one wants to do in the future, you should replace this by a homotopy co-limit. So the formalism is already prepared for this. And now you go through the construction, you generalize the arguments we have from Levin-Venn. The mapping class group acts on the stringnet space. It acts by changing the stringnets. This is a genuine action. This is not anomalous in any way. Yeah, so, and we are getting the Drinfeld center for the circle categories. And you can show that factorization holds, so we have a modular functor. Now, let's quickly talk about the cylinder categories, because cylinder categories are a thing many people are interested in. So again, what we do the standard thing, well, we take as objects, we take circles, decorated circles with finitely many points of them, and the morphisms are string nets between them, and if you're stacking the string nets, that gives you a composition of morphisms. Everything is completely geometric with the right decoration data. And if you have manifolds with boundary, which we want to do for boundary CFT, then we use that, technically speaking, these categories are pointed, they have a distinguished object. This here has a single object, which is distinguished, the other one has the monoidal unit as a distinguished object. And then, if we want to work on a boundary interval, then we put the monoidal unit to the boundary sides, and we compute a cylinder category, and we get actually back C itself, and we gain something. And this is another thing I want to advertise if you're thinking about topological field theories. We think about topological field theory that locality is obtained by cutting a surface, and that's one locality. But if you really think in terms of field theory, you want to have another locality, namely, as we all know, an interval embeds on a circle. So you would like to have, for a geometric embedding, a relation between the corresponding cylinder categories. And you have it. So you see that we start to have two different types of morphisms, surfaces and embeddings. Actually, there's a mathematical framework for this, double categories, and double categories fit very well pro-functors, just for the experts. So this is also an aspect I'm not reporting on here because it's a bit too technical, but it's a huge conceptual simplification. So then these cylinder categories have to be completed. Let's work for simplicity with an idempotent completion as people do this. Actually, working with separable Frobenius algebras is appropriate for idempotent completions. And then you can compute that actually the embedding of an interval to a circle induces the functor from C to its Stringfeld center, which is the left, and since we are unimodular, also the right adjoint of the forgetful functor. So all this works out nicely, and we can define stringnet spaces. And a last remark, and then we go to CFT. If C is a pivotal fusion category, this can be extended to a 3-to-1 TFT, and that's exactly derived, as you know it from textbooks. Good. And there's factorization, and we get an open-closed modular functor. And now I want to go to CFTs. And I'm writing here RCFTs, they are generalizations. I'm not discussing them just for time reasons. So we start with our worksheet. It's decorated by Frobenius algebras, bimodules, and couplings between bimodules. Then, well, what I can do is, this is a graph which I have to complement it a bit if I have boundaries by using these distinguished objects. Well, and then I'm replacing here this blue phase by a Frobenius network. Well, you know, Frobenius algebras are very well compatible with triangulations. Pachner moves correspond to relations in Frobenius algebras. This is known for a long time. So what we do is we blindly compensate here the blue thing by a triangulation. And we will see that this compensates for the violation of the graphical calculus by the non-connected morphisms. Okay, so if you do this, you can compute as objects in the cylinder category very explicitly what are the objects. So if I'm starting from an interval which has here is just a boundary field, a boundary condition changing field, then I'm translating this into a Skein-theoretic language, and if you look at what this is an object in the cylinder category for the circle, which is C itself, and if you compute this, what this projector is, this is just the inner home. So for people who have read what people in my book call group called The Book, so Dimitri's book. This is an easy exercise. And now, for defect fields, you do the same. So suppose I have here such a defect field, then I go to the cylinder category, I convince myself that this is an idempotent, so it determines an object, and this is actually what you naturally expect. So we get the right objects, field objects. Now, you see, if I'm taking this worksheet, I'm taking the complemented worksheet to be correct, then this determines for me a graph. Well, it's not a graph because the surfaces are also decorated, the two patches. But the class of a graph gives a vector in the string net space. So every vector, every worksheet gives a vector in this space, which, because quantum doesn't have any precise meaning anymore these days, we call the space of quantum worksheets. I will actually explain why we do this. So this vectors, and you see that if you change a defect line a bit, this is coming back to your question, Kostas, if you change the defect line a bit, this will not change the vector in this vector space. Because our graphical calculus is invariant under small homotopies and even under global homotopies. So, and then we map this to the correlator, which is in this string net space, and this string net space models the conformal blocks. This here knows about the monotromies of the conformal blocks. And we know what factorization is purely in terms of this mathematical machine. Well, and now the following can be observed. So any correlator, which is a vector here, can be actually described in terms of a map which relates this string net space for the defect data to the string net space for the chiral data. So all this information on the correlators is hidden in this map, and this map is constructed from this Frobenius monoidal factor. And if you can encode all kind of informations into a single map and into the pullback by it, this is done what you do this to describe universal bundles in this. So that's why we call this map here the universal correlator. If you're interested to determine a specific correlator, just take its class in the worksheet and go back and use the universal correlator. So now comes the following theorem, which is, well, it's not work in progress, but the write-up of the work is work in stagnation at the moment for lack of time. This linear map here is an isomorphism. What does it mean? If you consider sufficiently many situations of defects, then you will effectively use all the conformal blocks which arise as solutions of these differential equations. So there are no spurious solutions of the differential equations which are not used in some CFT situation. Of course, bulk fields, just on their own, they are too few. But if you use all defect fields of all kinds, then you are using all conformal blocks, and the word all is to be meant in the sense of vector spaces, so the linear spans are equal. Good. And conversely, what you can see is the CFT, if you look at the correlators, they can at best, they precisely measure not what is your worksheet, they are blind to what the worksheet is exactly, but they only measure the class of the worksheet in this space of quantum worksheets. That's the only thing the correlators of the quantum theory can see. Yeah, so, of course, we know this because if you have here an invertible defect, you would expect that these two give the same correlator. Yeah? But we have now a precise mathematical recipient which tells us what are the things you can really observe by studying the correlators of a CFT. And if you go through all situations here, you're getting all solutions of the chiral word identities. So this is a CFT insight. Maybe it has been gained by methods which look to you strange or unfamiliar, but it's definitely a CFT insight. Now coming back in the last 2 minutes or to the mapping class group. This is the situation I've sketched in the on the blackboard. Now they have the same correlators; they cannot be distinguished. Now the Dane twist here is obviously in a geometric mapping class group, but here not. Is it now in the mapping class group or not? Well, what is now a natural definition of the mapping class group is, since what matters of the worksheet is this vector in the space of quantum worksheets, we should take the stabilizer in the mapping class group of this space of quantum worksheets. And then the Dane twist, if you take the class of this modulo the Skein relations of the defect graphical calculus, then the Dane twist is in it in the sense that it preserves this this worksheet. If you do this Dane twist, and then you can compensate by local moves in your graphical calculus. And then the correlators are invariant under the mapping class group. And this mapping class group, if you've just found bulk fields, it's invariant under the ordinary mapping class group you would expect. Same for boundary fields. So we have invariance under the mapping class group, and we can also show factorization. And I'm not going to show factorization for you. Now, for the formally minded, we have two graphical calculi. Actually, this should be a diagram in not in bicategories, but in double categories. And then a CFT is actually such a natural transformation. The universal correlator fits in this. A pseudo-natural transformation has two components. One are the fields, one are the correlators. Everything fits into standard mathematics. And now you can start to upgrade symmetric monoidal to double categories. I briefly mentioned this, and functors and pro-functors. And I should say that there is a further upgrade, which I'm not discussing. In Sakura's talk, we have seen defects between two different three-dimensional TFTs. So you didn't see the three-dimensional TFTs here because I've tried to hide them, not to be tempted to use the full power of three manifolds, because I won't have it algebraically for non-semi-simple categories. Well, effectively, it's there in a setup which Laurens and Frank know very well, which we used in our paper for stringnet space. It's showing up in a holographic situation where you have a boundary and another boundary, and you construct a defect which separates a TFT, which is based on these bicolored diagrams to the ordinary ones. How do you construct this? Well, you wanted to have, Sakura, in your talk, very special defects, because you said the ultraviolet is fixed, and you do something in the infrared. Here we also want to have a very special thing, namely we want to have the chiral data on one side, and we can use the Frobenius monoidal functor to produce something like a defect. Now you have to set up what is a defect. I know how to set up the theory. I haven't worked it out simply for lack of time. It will be effectively done by the pro-functor versions of two functors. The theory is there, one has to work it out. Yeah, so all this is natural mathematics that's there today. And let me summarize. So I hope you see that these stringnet constructions are a very natural home for these constructions, that the bicategorical stringnet construction is quite important because it captures symmetries of the correlators, it captures relations between the correlators. By taking a worksheet, looking at its class, I'm getting relations between different worksheets which translate via the universal correlator into relations between the correlator. And so this is another important point. And then as an outlook, well, we didn't set this up for rational CFTs because rational CFTs are understood by now for more than 20 years. Understood at this level, yeah. And to go beyond semi-simplicity, all here can be extended. I never require that the underlying categories are abelian, and cylinder categories are naturally not abelian. Now, if you want to go beyond finiteness and have infinitely many simple objects, then your field objects still exist, but they will exist in certain pro or incompletions. You need a bit more category theory for this. You want to go beyond rigidity. That's a very hard problem, but it's also something you will be able to do in this setting. And finally, secretly, the whole formalism is set up that we can replace quotients, which are co-limits, by homotopy co-limits, and we can do homotopical versions of this, but of course this requires a much bigger toolbox, and personally this is not my first priority, but all this is now, the ground is ready for all this. Thank you very much.
Any questions? I have a question. How do you think about unitarity in this formalism? The additional structure you have to put in and then make everything compatible with that?
Unitality.
Unitarity.
Unitarity. Well, I'm not thinking about unitarity at all, to be honest. I'm replacing unitarity by pivotality.
Right.
And pivotality means that the double dual is trivial. And why do we do this? Because CFT has lots of applications which are not unitary. If you want to apply it to problems like, for example, percolation, this is definitely not a unitary CFT. Yeah, then you should develop tools which are appropriate for this. I can give you a bit of a different answer. If you want to unitarity in the sense of star structures is not completely ready to work with categorical structures. So for example, if you set up a three-functor formalism for star algebras, then you get something which are almost adjoints, but they are not really adjoints. If you look at the tensor product of Hilbert spaces, the tensor product of Hilbert spaces is famously not a tensor product in the sense of category theory. It has only a universal property for Hilbert-Schmidt operators. So that's why I'm quite reluctant to go to the star world. If you analyze what's going on in the star world, then really they have not enough morphisms. And I think the category has to be enriched in some topological category again. But well, this is nothing I will probably do in the next couple of years. Other people will do this. So, for example, Clausen and Scholze have some ideas on topological theories, and I expect that there will be developments in the next 5 years.
One question, given some simplicity. What would be replacement sort of separable continuous? Separable algebras in non-semi-simple case, it's not a Marita invariant notion.
Exactly.
You use this visual definition of separable algebras. So
yeah.
What would be a good replacement for that?
So what we should do then is you work with pivotal module categories.
Mm-hmm.
But you need a bit more because you want to relate it to a different word. So you need something like a fiber functor. So you need a reconstruction. So you need an algebra. We know that this will be an exact algebra in the sense of a recent paper of Eddinghoff and Coulombier and these people. And we will then work with pairs which are these pivotal, which will be these pivotal module categories represented by such an algebra. And then we have again a forgettable functor. what I should point out for the logarithmic people in the audience is you have to be careful how to set up your input category. And I should emphasize the input category is not necessarily abelian. So I think the correct input category is, also the cylinder category is not abelian. Quantum topology doesn't want to have abelian categories, I'm claiming. So what you should take is, you should only work with the projectives, then you will work with the modified trace. That's the natural thing to work then with. And the price to pay is that things are in the end not unital necessarily anymore. But nobody, or maybe people wished for unitarity, but they never paid for the order. Unitality of the object. And we know that in other CFTs like Liouville type theories, there's not necessarily a monoidal unit. It's not necessarily one of the bulk fields.
So I know that you're always very precise with definitions. You used quantum. What does it mean for you, quantum?
Quantum means that I'm studying the situation on the worldsheet, which a priori is a classical geometry, a Riemann surface with lines and so on. I'm studying it only via what the correlators of the CFT can see. So I'm not saying I can distinguish whether a defect line runs like this or runs like this, but the only thing I'm seeing is really what I can see in the correlators. And that's the statement that the correlator factors over this space means that only what use the image of the worldsheet in this space. This is the only thing you can really observe by observing correlators. And correlators, well, let's call correlators quantum. Of course, there are situations where correlators of CFT are not quantum in the sense of physicists. And that's why I made this remark that quantum doesn't have too strict a meaning.
Can you also, when you go beyond finite number of symbols, then study like holographic CFTs?
If the question, if can you in your question is strictly to be taken in the present tense, then I have to say I haven't done this at the moment. Yeah.
But you expect that you can take this beyond finite, say, also, you know, countably infinite many versus uncountably many.
Yes, and a simple test case, which is already challenging if you want to do it in a clear way, is take the uncompactified free boson.
Yes, I'm actually going to ask whether the X boson.
Yeah, and for the
nice logarithm.
Yeah, and we have very preliminary results that if you take the uncompactified free boson, you will realize the field object as an algebra in a Yoneda completion. Now, a Yoneda completion is very akin to an int completion. There's also a pro completion. Actually, in a full formalism, I expect that you have to use both. Then you will have something which, where you have an algebra structure in one category and a co-algebra structure in the other category. This is quite natural because we distinguish in and out. And this is a structure which people have worked out and used extensively in linear logic. So they have these two categories are called, the pair of these two categories is called the dialogue category, and people like Paul-André Méliès have studied this. So we are not going into unknown, completely uncharted mathematics.
Maybe one final question then, because we still have the break.
Please go on. No, I have it's an orthogonal question. I'll ask you afterwards.
I'm curious, in the last slide you mentioned the difference between chiral CFT and full CFT in your language, right?
Yeah.
A typical thing that, one thing that happens when you go to chiral CFT is that you see causality, because in over time and space, in your language? Okay. What is
Well,
causality?
Causality needs, to make a quick answer and for the benefit of coffee break, causality means a metric.
Yes,
And
space-time, right?
we are working here in a formalism which is purely topological. And that explains, in a sense, why structures people have seen in Euclidean TFT and in Euclidean CFT, but also in CFT in the operator algebraic approach, are so close. So this, the mathematical structures we use are agnostic to the metric.
Okay. No further questions. Let's thank Christoph again.